Everybody, today we're going to be taking a really good deep look at graphs. So I want to take today and next time and really go through the math of what a graph is, why it's important, and go from there. So what I want you to do, and I'm going to be collecting this, so make sure you do it. I want you to take a minute, write down everything you know about graphs. Go ahead and pause the video, take 1 to 2 minutes. Write down everything you know about graphs on a piece of paper. Go ahead and do that now. Okay, so now you've done that, what I want you to do is I want you to box that off, okay? Because that's our starting point. That's what you already knew about graphs. And it could be anything. It could be things like graphs have, X and Y axis. We talk about domain and range on graphs. It could be anything you wanted about graphs. There were no wrong answers here as long as it had to do with graphs. So what we want to do today is we want to look at some of those key features of graphs. And we're going to look at polynomials today. The goal, though, is to take what we did in Unit 6 and apply rationals to what we know about graphs and add a few new things that maybe you haven't seen before or at least not named before. So that being said, let's go through these. Now, when I go through these today, when I talk about domain, especially with my regular students, I usually just say the X's that can work. And that's not wrong, but it's not a perfect definition. It's not encompassing using that math academic language that we really want to be using, especially in the honors classes. So let's rewrite this and let's put this in a little bit better way that works, again, with that academic language. So what it really is, what domains are, is the set of real numbers. And it's important that we're looking at the real numbers here. Can we look at other planes where the complex numbers pop up? Sure. But today we're just going to be looking at the real numbers, okay? And for this unit, we're going to be doing that. You'll get more into the complex plane if you continue your career in math and get into Calculus 2, Calculus 3. But it's the set of real numbers such that f of x exists. Okay, what that's saying is it's the x values I can plug into a function and get a solution. So remember with things like square roots, right? We couldn't do negative square roots in the real plane. And then things like dividing by 0, we couldn't have either. Okay, but for polynomials that we're going to be looking at today, parabolas, things like that, it's going to pretty much work all the time for us. Absolute values work, things like that. Okay, it's range, though, that doesn't always give us all the solutions. So this is the set of real numbers. That is produced by the domain. Okay, and again, we want to only look at the reals here. Okay, we're not going into complex right now. We're not dealing with any of that. We're not dividing by 0. We're just looking at the real numbers. So it's a set of real numbers that are produced by the domains. Now, we did this a little bit differently with the Big Ideas program on how we wanted to present this data. Today, though, I want to show you the 2 ways that you're going to see it, at least at Copper Hills. And most likely in your future, if you, again, continue down the math path. So you're going to see it in 2 different ways. You're going to see an interval notation and then standard notation or inequality notation. So interval notation says, hey, where does it start? Where does it end? And we got those parentheses and brackets. Well, my domain here on this function works on all numbers. Okay, I know it's going up faster than it's going left and right, but eventually it's going to go left and right. So my domain starts at negative infinity, and it goes to positive infinity. This is that interval notation. Okay, again, depending on which class you're taking. If you're taking 1050, 1060, they're going to do they're going to use interval notation. You see it a lot upper level mathematics as well. For AP Calculus, though, they're going to look at it from inequality notation or standard notation. So for inequality notation here, since it's just all real numbers, that's all we would write, all real numbers. Okay, now for the range, it's a little bit more obvious what's going on with that inequality notation. So let's look at the range. Okay, well, the range is the set of numbers that is produced by the domain. So it's the y's. Well, my lowest y here is at this vertex, and that's going to be at 2, -8. Specifically, the -8, because again, this is probably one of the times we're actually going to look at y's. So that being said, my lowest y that I ever get is -8. And my biggest y, because it does go up to infinity, is going to be infinity. Now, we never get to infinity, so anytime you have infinity or negative infinity, you're always going to use a parentheses because you can't actually get there. For the -8, though, we need to decide, are we including that -8 or are we not including it? In this case, the -8 exists. It's there. So to include it, we're going to use a bracket. Now, my inequality notation here would be y needs to be greater than or equal to -8. All the y's that are produced are greater than or equal to -8. There's not going to be anything at -9, -10, -100, negative infinity. There's nothing down there. It has to be -8 or bigger. Okay, and again, it can be -8, so we do want to include that or equal to. For x-intercepts and y-intercepts. X-intercepts are one of those things in math where they pop up a lot. And it's one of those things that you probably have heard, and it's probably just been called something else. X-intercepts can be called zeros, solutions, answers. Okay, they give us factors if we're dealing with a polynomial. But how we display that information depends on what we're asking for. If we're asking for an x-intercept, it's always going to be x0. It's a point. Zeros are written as x equals something, same with solutions. And then factors are written as x plus or minus our answers. Okay, so what is an x-intercept? Well, an x-intercept is a point, and again, it's important that we say it's a point. Oh, let me fix that, sorry. Where f of x is equal to 0. Okay, and really it can be point or points. I can have more than one. A y-intercept is a point at f of 0. So I'm taking 0, I'm plugging it in. That's always going to be represented as 0, y. Now, it's important to note here, as long as it's a function, it will be a point, not points. Okay, because again, that vertical line test, right? If it's on this y-axis, I can't have two spots that work, assuming it is a function. Now, can I have a graph with multiple functions? Sure. But within each function itself, I can only have one y-intercept, assuming, again, it's truly a function. Something like this is not a function. It fails the vertical line test. Okay, now the nice thing about a y-intercepts and x-intercepts and y-intercepts is only one way to write them. So my x-intercepts here are going to be -2, 0, and 6, 0. Y-intercept, is going to be 0, -6. So again, only one way to write these. Okay, increasing, decreasing. Now, we have to be kind of hand wavy here a little bit, because when I'm about to describe increasing and decreasing, it's where a function has, because if I talk about points on a function, I can't talk about the next point, because between 0 and 1, there are answers. Now, if I'm talking about just the integers, 0, then 1, then 2, then 3. But if I'm talking about all the reals, I can't just go from 0 to 0.000001, because there's numbers between those. And I could keep going on forever. Let's, look between 0 and 1. Okay, well, 0.5. Well, what's between 0 and 0.5? 0.2. And I can keep doing that and doing that and doing that and cutting in half over and over and over again forever. And I'll still have a number between 0 and whatever that number is. So we need to be a little hand wavy with this definition without going into tangents, which we haven't really talked about yet. We're going to be doing that next unit. So because of that, what we're going to do is we're going to say, okay, well, let's assume we could find the next point. Again, technically we can't, but let's just say we can for right now. So if I have 2 points, so it's the set of real numbers, again, it's important to specify real numbers. Where the previous point is less than, previous point's output. Let me be more specific. Point's output is less than the current point. Okay, now again, I know we have to be kind of a little bit hand wavy here. So what that's saying is if I have a point here, because I can see graphically that this is increasing on the right side. Well, if I look at the point just before it, okay, and I realize that's not right just before it, but if I could, it would be slightly less, even minusculely less than the one I'm on. And I can keep going back until I hit this vertex. Now, I can't include that vertex, because at that vertex, if I go back a point, and again, hand wavy here, then the previous point is greater, or the output of that point is greater than. So I don't include the vertex. I need to be careful, though, when I talk about this in the other direction for decreasing, because it's a set of real numbers. And again, once we get to tangents, we'll come back and rewrite this definition because it's a little bit clearer there. It's a set of real numbers where the next point's output is less than the previous. Or current point. Meaning, again, going down from here, my next point is a little bit less, until I get to that vertex. The vertex is what we would call a constant point. And again, this becomes a little bit easier once we get into tangents, but the idea is that it's neither increasing nor decreasing. So for increasing and decreasing, we do have the two increasing, decreasing. We do have the two notations again. So let's do both. And on your assignment, I do want you to do both, just so you're getting practice for both ways. So this is increasing, and we want to look at those inputs. So it starts at 2, because 2 is an input here, and it increases until infinity. So 2, infinity. Now again, we can't ever include infinity, and we're not going to include 2 because at that vertex, it's not doing either. So over here, we would say x greater than 2. We don't want to do equals because, again, we're not including that 2. Decreasing, we're going to go from negative infinity to 2. Again, not including either of those points because we can't get to negative infinity, and we're not going to include 2. And here, x needs to be less than 2. Now for constant, we would say for interval notation at 2. And for standard notation, we would just say x equals 2. Okay, positive, negative. Positive and negative is the set of real numbers where f of x is greater than 0. So when I plug a number in for x, the function should be positive, greater than 0. Again, we're not going to include 0 because 0 is neither positive nor negative. Conversely, the set of real numbers where f of x is less than 0. Again, 2 notations here. Oops, let's just make that blue so it matches what I'm about to do. So my positives are up here. And I do have 2, and that's fine. You can have 3 or 4 or 5 or whatever. And my negative is down here. Now, again, I'm not going to include those x-intercepts because at those x-intercepts, it's at 0, and that's not positive or negative. Okay, still 2 notations. So and we're going to use those x values, those input values. So from negative infinity to negative 2, not including, because at negative 2 it's 0, not negative, not positive. And then also from 6 to infinity. Now I want to put a union symbol here because that tells me it needs to be either one of these or the other. It doesn't have to be both at the same time. For the other, we're going to say x is less than negative 2. Again, not including it. Or x is greater than 6. For my negatives, we're going to go from negative 2 to positive 6, sorry. And this is the one that throws people off, okay? So x needs to be greater than negative 2, but it needs to be less than 6. So anytime you have it where it when you have 2 definite sides, we need to make it look like this. If it's going off to infinity, I don't really need to say that x is less than infinity here, or greater than infinity, negative infinity. It doesn't really make sense to add that. Of course, it's going to be that, okay? It just needs to be less than negative 2. Okay, relative min and relative max. A relative min is the set, or sorry, not the set of numbers, oops, the point where a function goes from increasing to decreasing. Oops. And a relative min would be the opposite. The point where a function goes from decreasing to increasing. Okay, now a function doesn't have to have these. We'll look at one in a second. The one we have, it only has one of these. So if I look, relative max is going from increasing to decreasing. Well, at no point is this thing increasing and then decreasing. It decreases and then increases. So I have something down here, but this is going to be a relative minimum. Okay, and that's going to be at 2, -8. Only one way to write these. For the relative max, It does not exist. Okay, do I have an absolute maximum? Yes, that's at infinity. But I don't have a relative minimum or maximum. This function never increases and then decreases. Okay, going left to right. As I go left to right, I'm decreasing and then I start increasing. Okay, I never come back down. If I came back down, that would give me a relative maximum. And you can have more than one of these. If I had a function that did this, I'd have two maximums. Okay, again, relative maximums and one minimum here. Okay, last thing, end behavior, just really quick on this. Limit as x approaches negative infinity, f of x equals what? Okay, so as x is going to negative infinity, where is f of x going? And then we also want to look at the other side, end behavior, so, both ends. F of x, where does it go? Okay, now this is the notation you're going to see in pretty much every class moving forward. So my limit as x approaches negative infinity, as I go left, I'm going up to positive infinity. As I go right to positive infinity, as I'm going right, I'm still going up to positive infinity. Okay, and for polynomials are always going to go to positive infinity or negative infinity. But that's not true for all functions. And next time when we look at rational functions like we did in Unit 6, you're going to see that that's the case. Please, again, make sure you keep, here's what I want you to do. I want you to take your sheet that at the beginning of class, the starter, where I had you write down all you know about graphs. I want you to add to that list now. Okay, please box off what you had at the start. Okay, again, no shame, no nothing here. I just want to see where you started and what you've learned. Okay, you're not going to get a higher or lower grade for having more or less things at the start. Again, what I want to see is what all you've learned, where you started, where you ended. Okay, to make sure that you're getting all the parts. That is going to be for a grade, so please don't lose that. So take some time, add the things that maybe you forgot about or learned today, and then work on the 3 other graphs on the assignment. If you have any questions, make sure you're asking for help, getting on for RTI Fridays. Again, you can get on Zoom for that. Link is on Canvas. Let me know if you have any questions and see you next time.